Welcome back to Calculus 3. I'm Dr. Jeff Groh, and today we're going to talk about vector-valued functions. Vector-valued functions have their domain being contained in the set of real numbers, but they output vectors in Rn for some n. There's a usual notation for these. Let's suppose that we're working in R3 for the moment. We'll have a vector-valued function. It's r of t with a little half arrow over the r. It's going to output x of t, y of t, z of t. So the x, y, and z coordinates are all functions of some parameter t. These are parameterized curves. They'll sweep out some path in R3 in this case. We have 1 degree of freedom, the parameter t. X, y, and z will depend upon that. They will have an orientation. That's the direction that the curve is being swept out. From here till the end of the course, there will be a clear progression. We'll start with vector-valued functions. Their domains are in the set of real numbers, so we can think of them as one-dimensional objects embedded in an n-dimensional space, i.e. curves. We will then progress to functions having a domain that is contained in Rn and outputs real numbers. An example might be z is a function of x and y. If you have a function that maps some set contained in R2 and outputs in R, as in this case, then that gives you a constraint on the three variables. You end up with an arbitrary free choice in x and y, but z will be determined by those two choices. You end up with a two-dimensional object embedded in a three-dimensional space. That's called a surface, in this case, or a hypersurface in higher dimensional spaces. We will end up talking about functions that map some domain in Rn but output vectors. These are going to be vector fields, so this is a plan for the rest of the term. We will, of course, begin with the vector-valued functions, or curves. Let's begin with a simple example. R of t equals cosine of t sine of t. You can see here we're setting x equal to cosine of t and y equal to sine of t. This is obviously a parametric curve, and it satisfies x squared plus y squared equals 1 due to the Pythagorean identity, which means we have a circle of radius 1. But it's more than that because of the parameterization. Parameterization gives you an orientation as well. If t is equal to 0, we're at the point 1, 0, right here. As t goes into the first quadrant between 0 and pi over 2, both cosine and sine are positive, which means you have to trace this curve into the first quadrant. That means the curve must be traversed in a counterclockwise fashion. If we have x squared over 9 plus y squared over 16 equals 1, we can describe that by the vector valued function 3 cosine of t 4 sine of t. For straight lines, before we described those as some vector x naught plus t times a vector v, which goes in the direction of the line. I guess we can describe those now in pretty much the same fashion. For our next example, suppose we have r of t equals cosine of t sine of t t. You can see if this didn't have that last coordinate, it would just be a circle of radius 1 in the xy plane. But as t increases, z increases. This curve is going to cycle upwards. As t increases, z increases, but it's going to go around and around the z-axis. What would you name this curve? That is a helix, a little corkscrew curve. Now I want you to think back to Calculus 1. The progression was limits followed by derivatives and then integrals. We'll have to go through this progression for each of the classes of functions mentioned earlier. Before talking about limits for vector-valued functions, let's review the concept from Calculus 1. What did it mean to have the limit as x goes to a of f of x equal to L? It meant given an arbitrary epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus a is less than delta, which gives you a measure of distance between x values in a being smaller than delta but bigger than 0. Bigger than 0 because we are specifically ignoring what happens at x equals a. If you get close in the domain, closer than delta, then the distance between f of x and L will be smaller than epsilon. Yep, the epsilon delta definition of limits from Calculus 1. Now let's see what is necessary to change in order to have a notion of limit for vector-valued functions. These vector-valued functions map some domain in the set of real numbers into the set of vectors in Rn. So we'll do the limit as t goes to, say, t naught of r of t equals, it has to be a vector-valued limit because you're outputting vectors. So we need a measure of closeness between vectors. The domain is still real numbers. So given epsilon greater than 0, there exists delta greater than 0 such that 0 is less than the absolute value of t minus t naught is less than delta, then the norm of r of t minus L is smaller than epsilon. Yeah, you have to use the norm to calculate distances between these vectors in the range. So this is the only new thing. So Let's look at the following idea. Suppose that we have the limit as t goes to t naught of r of t equals L, and L is the vector a, b. Then, given epsilon greater than 0, there exists delta greater than 0, such that if 0 is less than t minus t naught is less than delta, then epsilon will be greater than the distance between r of t and L. That's the square root of x of t minus a quantity squared plus y of t minus b quantity squared. Now wait a minute, we're going to play with this a little bit. If you ignore a positive term under that square root, you will get something smaller, or equal to, if it's 0, the square root of x of t minus a quantity squared. But what is the square root of x squared? It's the absolute value of x, not x. Get this one straight. Think about it. So we get the absolute value of x of t minus a is less than epsilon. That implies, in the sense of limits from calculus 1, that the limit as t goes to t naught of x of t equals a. Similarly, the limit as t goes to t naught of y of t equals b. This tells us something really interesting about limits. It tells us the following theorem. If we're calculating the limit as t goes to t naught of x of t, y of t, you may as well calculate the limit of each coordinate separately, provided those limits exist. We've just reduced limits of vector-valued functions to the notion of limits that we introduced in Calculus 1. That's going to save us a lot of work and time. Let me give you an example. So suppose I'm calculating the limit as t goes to 0 of the vector-valued function. Let's do sine t over t. How about 1 minus cosine t over t? And then let's do, how about e to the t minus 1 minus t over t squared. To calculate the limit of the vector-valued function, I just need to calculate the limit of each coordinate separately. Well, that's good news because you know how to do those limits. The bad news is one problem is converted into 3 or 4 or however many dimensions you're working in. So in this case, when we take the limit in the first coordinate, you might remember what this one is. As t goes to 0 sine t over t, what does that go to? One thing you need to remember, if you just plug in the 0 and get sine of 0, 0 divided by 0, 0 divided by 0 in the context of limits means more work. In particular, this is a L'Hopital's rule case. The derivative of sine is cosine, the derivative of t is 1, cosine of 0 is 1, 1 over 1, the value of the limit is 1. And I always ask my Calculus 1 students to memorize this particular limit and the next one. Do you remember the value of the next limit? If not, calculate it using L'Hopital's rule. It too is a L'Hopital's rule case. You'll end up with 0. On the last one, it too ends up being a L'Hopital's rule case. E to the 0 is 1. 1 minus 1 is 0 minus another 0. All divided by 0 squared. You get 0 over 0. More work. Well, L'Hopital's rule says take the limit as t goes to 0 of the derivative of the top over the derivative of the bottom. You still have a L'Hopital's rule case because it's still 0 over 0. So we'll take the derivative again. The derivative of the top divided by the bottom. Now as t goes to 0, we'll have 1, 0, 1/2. P sec h. Do you remember what it meant in Calculus 1 for a function to be continuous at some point? In Cal 1, f is continuous at x equals a if you had to have 3 conditions hold to be continuous at some point. First of all, the limit as x goes to a of f of x must exist as a limit. 2, the function value at a must be defined. And 3, and most importantly, in the limit as x goes to a of f of x, you get f of a. Guess how we're going to define continuity in the context of vector valued functions? It'll be pretty much the same thing. A vector valued function R is continuous at t equals t naught if 1. The limit as t tends to t naught of R of t exists. 2. R of t naught is defined. And of course, in the limit as t goes to t naught of R of t, you get R of t naught. Now that you know about limits of vector valued functions, it's time to start talking about derivatives. First, a review from Cal 1. The derivative of a function at x is defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Yes, the change in y divided by the change in x in the limit as the change in x goes to 0, the slope of the tangent line. How do we define this context now in the case of vector valued functions? We, of course, define the derivative to be the limit as h goes to 0, r of t plus h minus r of t all over h. So what's going on here? What are we getting from this? Suppose our curve, r of t, is maybe something like this. For a small increment in t, say h, you'll end up subtracting these two little values. If you divide by a small value, you end up with a vector like this. If you think of r as a position vector in space, This is the change in position vector divided by the change in time. Of course, rate is distance over time, but this is directed, so it's better than that. It gives you the velocity vector. The velocity vector will be a tangent vector to the curve. The velocity vector will be a tangent vector to the curve. Velocity is the instantaneous rate of change of position with respect to time. This is also sometimes denoted as r dot. Newton's notation for derivatives with respect to time was a dot, not a prime. Now, limits happened coordinate-wise. Do derivatives? Let's find out. Let's look at r prime of t. Okay, it should be a dot, but I'll write it as a prime because I'm not necessarily thinking of t as time. It's just a parameter. It's the limit as h goes to 0, r of t plus h minus r of t over h. Now, according to the limit rules, you can take the limit of each coordinate. It's going to be x of t plus h minus x of t over h, comma. Let's just do 2 dimensions. This works in arbitrary dimensions. And sure enough, you get dx dt, dy dt. So to calculate the derivative of a vector-valued function, all you have to do is take the derivative of each coordinate. However many coordinates you need. Suppose our function is the circle cosine t sine t, circle of radius 1. Then what is r dot? Well, it's minus sine t cosine t by the last theorem. Now let's think about this. At t equals 0, the position vector is 1, 0. That puts us right here. But at t equals 0, the velocity vector is 0, 1. Straight up. What about the velocity at t equals pi over 4? The position vector will be right here with an angle of pi over 4 off of the positive x-axis. We'll have negative root 2 over 2, positive root 2 over 2. So we have a positive y-coordinate but a negative x-coordinate, which gives us a velocity vector right here. Notice it's tangent to the circle. At pi over 2, the position vector will be 0, 1, placing us right here. The velocity vector will be negative 1, 0, putting the velocity vector right here. So you can see that the velocity vector will be tangent to the curve and pointing in the direction that the curve is being traversed. Now that we have a new object, the derivative of vector-valued functions, we need a theorem telling us the algebraic properties. When you take the derivative of the sum of 2 vector-valued functions, you get the sum of the derivatives. Well, that shouldn't be very surprising. So that's the nature of the derivative in the presence of the addition of vector-valued functions. Similarly, if you have the constant times the vector-valued function, then you get a constant times the derivative. So constant factors can be pulled out of the derivative of vector-valued functions. Oh, by the way, minus works the same as plus. Now, if you have the derivative of some function of t times a vector valued function. How does that work? Well, it turns out there is in fact a product rule. These are called Leibniz rules. Any product rule is called a Leibniz rule. It's the derivative of the first times the second left alone plus the first times the derivative of the second. Go figure. You might have guessed. We have another operation that's like a multiplication called the dot product. What if I'm taking the derivative of r dot s, the Euclidean dot product of two vector valued functions? Do you still get a Leibniz rule there? And the answer is yes, or else I wouldn't have brought it up. It's r of t dot s plus r dot ds dt. We do have a couple other operations to think about. What about the cross product? On this one, you need to be careful. The cross product is not commutative. So the order in which you write the factors makes a difference. It must be in the form dr dt cross s plus r cross ds dt. So caveat discipuli, let the student beware. Write it in the correct order. You should have remembered the product rule in this order from Calculus 1. If you didn't, go back and memorize it in this order. For non-commutative products, it has to be in this order. Now, what about the derivative of the norm of some vector valued function? How do you take the derivative of this? I'll tell you the answer, but you won't believe me until I prove it. It's going to be r dot dr dt over the norm of r. That certainly requires some proof. Let's prove the last property first. Let's take the derivative of the norm of the vector valued function r. That is the derivative of the square root of the dot product of r with itself. We'll recall the theorem that the norm of v is the square root of v dot v. That being the case, you should also remember that the derivative of the square root of x is 1 over 2 root x. I want you to just memorize this and have this available at very quick recall. So this is going to be 1 over 2 times the square root of r dot r. But then you have to multiply by the derivative of the inside, r dot r. And that's where you need to apply a Leibniz rule. By the Leibniz rule for the dot product, this is the norm of r, 1 over 2 times the norm of r, you'll have the derivative of the first dot the second plus the first dot the derivative of the second. Now, while the cross product is not commutative, the dot product is. So we can just double the first one and cross out the second. The 2's will then cancel and we'll be left with r dot dr dt over the norm of r. We probably should prove at least a couple more of those properties. First, suppose that r is xy and s is ab. then r dot s is xa plus yb. So what is the derivative then of r dot s? Well, we take the derivative with respect to t of each of these scalar valued functions. Now, those being scalar valued, all we have to do is apply the product rule from calculus 1. It's going to be x dot a plus xa dot plus y dot b plus yb dot. Now, if we collect the terms that have a dot on the x and the y together, that's going to be r dot dot s, and then the remaining terms will represent r dot s dot, proving the product rule, the Leibniz rule, for the Euclidean dot product. The claim that requires special justification because it makes a special claim about the order is the Leibniz rule for the cross product. Let's suppose R has coordinates a, b, c, and S has coordinates x, y, z. All of these are functions of the parameter t. Then we get the derivative of, how do you calculate the cross product? It should be bz minus cy, and then minus az minus cx, and then ay minus bx. The derivative can be calculated coordinate-wise. So, on the first coordinate, we require two product rules. That's going to be b dot z plus bz dot minus c dot y minus cy dot, and then minus a dot z plus az dot minus c dot x minus cx dot, and then a dot y plus ay dot minus b dot x minus bx dot. Now, if we collect all the terms in these first coordinates that have the dots on A, B, and C, you'll see that we'll get the same expression that we had to start with for R cross S, just with all the coordinates of R being dotted. That gives you R dot cross S. But you can break out all of the remaining terms into a separate term, and all of those have dots on X, Y, and Z. That gives you R cross S dot, and that ends the proof. Now, I would like to look at a special example called the cycloid curve. The cycloid curve is the path of a dot on a tire as the tire rolls down the road. Let me derive a vector-valued function formulation for the cycloid curve, but I'm going to do this in steps. First, I'm going to assume that the tire is stuck in the axle, up to the axle in mud, and just spinning around clockwise. We'll have x equals, let's let the radius be r, r sine t, y equals r cosine t. X gets the sine and y gets the cosine because you're moving clockwise. Now, on the next step, I'm going to move the tire up. Just a vertical translation. That doesn't change the x coordinate at all. What it does is it adds a radius to the y coordinate. We're just having this thing peel out in place without the wheel going forward. It's in the next step where we send the wheel moving forward. It's going to change x position, but with time. That doesn't change the y value at all. What changes is the x value. It's going to be r times t plus r sine t. We're translating the wheel forward. How much? When t is equal to 2 pi, we've made 1 revolution. And in that much time, we've gone through 2 pi r translation, 1 circumference. So we send the tire forward 1 circumference every revolution. That's in good contact with the ground. That gives us a vector-valued function for the cycloid curve. It is the constant radius r times t plus r times the sine of t, and then r plus r cosine t. Now, this curve, as we've seen already in this course, is not smooth. Remember, the curve r of t equals x of t, y of t is smooth if x of t and y of t are differentiable, but that's not enough. You recall, these are not only differentiable, they're infinitely differentiable, and even better, they're analytic. So you have to have the other condition that the speed is not 0. The speed of a vector-valued function is the norm of the velocity vector. If the speed is not 0, then it won't have a chance to stop, turn on a dime, and take off in a new direction, like the cycloid curve. We may as well make it official. Speed is the norm of the velocity vector. It's the rate of change of arc length with respect to time. Do you remember how we normalize a vector? If you take a vector and divide it by its norm, you end up with a unit vector that points in the same direction. So this is parallel to the vector v because it's just a scalar multiple, but it always has length 1. To normalize a vector means to find a unit vector that points in the same direction, and that's done through this process. From this, we'll make a definition. The unit tangent vector t to a curve r of t is, it's found, of course, by taking the derivative r dot and dividing by the speed, normalizing the velocity vector. The unit tangent vector always has length 1, obviously, since it's just arrived at through normalization. It's also always tangent to the curve because it's parallel to the velocity vector, which is tangent to the curve. Suppose the norm of some vector-valued function is constant. If the curve lies in R3, that means the position vector is always a constant distance from the origin. That just means whatever the curve is, it's on the surface of a sphere. If it's in R2, that just means the curve is moving around on a circle of radius c. What does that tell us then about the derivative? If we take the derivative of both sides, we know that the derivative of the norm is r dot over the norm of r. The only way a fraction can equal 0 is if the numerator is 0. R dot. Are you getting dotty already? But this is true if and only if the position vector is orthogonal to the velocity vector. Yeah, if the position vector is here on the circle, the velocity vector has to be tangent, which means at a right angle too. So we know how to calculate limits of vector-valued functions. We know how to calculate their derivatives. How do you integrate them? Well, let's suppose that r of t is x of t, y of t. Then the integral of r of t dt is, because I said so, angle bracket, the integral of x of t dt, the integral of y of t dt. In other words, you do the same thing you did with derivatives. You integrate coordinate-wise. The same is true for definite integrals. It is, by definition, the definite integral of each coordinate. I suppose that this is good news and bad news. The good news is we've reduced the integration of vector-valued functions to problems you already know how to solve. The bad news is every time I give you a single integral problem for a vector-valued function, it means you have to do more than one integral. Suppose we use the usual capital notation for antiderivatives. If I'm integrating x of t dt comma integral of y of t dt, we should get big X of t plus a constant and big Y of t plus an independent arbitrary constant, which we can call big X, big Y plus C1, C2. In other words, we'll get kind of a big R, antiderivative of the vector-valued function little r, plus an arbitrary constant vector of integration. That's how you handle that. You just add an arbitrary constant vector of integration. So let's do an example. Let's suppose we're integrating 1 over t squared plus 1, and let's do 1 over t minus 1. And how about 1 over the square root of 1 minus t squared? As you can see, the integral of the first coordinate is the 1. That's the one I want you to know. If you're integrating 1 over 1 plus x squared, that is the inverse tangent of x plus c. On the next term, the derivative of the bottom is equal to the top. Whenever I integrate f prime of x over f of x dx, by u substitution, I get log absolute value of f of x plus c. This is in that form. I'll get the log of the absolute value of t minus 1 plus a constant. I'm holding off on writing those constants. The last coordinate is the other one. This is the other one I want you to know. The integral of 1 over the square root of 1 minus x squared dx is arcsine of x plus c. So we get arcsine of t plus an arbitrary constant vector, one constant for each coordinate. Now, let's suppose that we know the derivative of r to be something like 2t, how about cosine t e to the t. When we integrate to find r, we'll know r up to an arbitrary constant vector. That arbitrary constant can be determined by the knowledge of r at one point. So if we know we get 0, 0, 1 at t equals 0, first of all, we know that if we integrate dr dt, t squared, comma, sine t e to the t plus an arbitrary constant vector. Well, 0, 0, 1 has to be r at 0. If we plug in 0 everywhere inside here, we get 0, 0, 1. And in this particular case, with this particular piece of initial data, that means the constant vector is the 0 vector. It follows then that r is t squared sine t e to the t. In physical problems where the position of a particle is completely determined by some acceleration function, you undo two derivatives with two integrals. You will in fact have an arbitrary constant of integration when you find the velocity. That constant of integration will be that constant of integration will be determined by the velocity at some initial value. When you integrate again to find position, you get another constant, and that constant is determined by some knowledge of the position. So if you know something about the position and velocity at some particular point in time, then you can determine the entire evolution of that particular particle, where it will be at any given time in the future and where it has been in the past. Similarly, if you could determine the position and velocity of every particle in the universe right now, you can predict the entire future of the universe as well as its past.